Vai canal ao feito. Consegue ver os lados. Não é bastante bem para falar. Dá para falar. Vai ter que publicar depois. Assim, perguntava que as classes não têm. Vocês falarem ali para o está a projetar no site? Está no site? Já atrasado bastante. Pá, podemos pôr ali, mas...
Boa tarde a todos. Atrás, desculpem o atraso. Obrigado por terem vindo. Welcome everybody for this second edition of our Industry 4.0 Big Data and Data Science. It's a great pleasure to realize this new edition. I would like to thank my colleagues that were involved in this event when I was doing it. João Pedro, Elder Quintela, which is up here. But I would like to thank especially to our speakers of today, Professor Goran Putnik from the University of Minho and Professor Peter Tala from the University of Ljubljana. Ljubljana is the capital of Slovenia, yes. So I hope you enjoy this event. We believe this is a relevant topic, not only for our master degrees, Master of Computer Engineering, but also for your degrees and for companies, of course, be here. So, Manel, it's all yours now. Thank you very much.
Thank you, Luis. Good afternoon. On behalf of the School of Technology, I address you all a warm welcome. Thank you for being here on the second edition of the week Industry 4.0, Big Data and Data Science. As you know, Industry 4.0 is a major challenge today, is a mobilizing challenge for the next few years. That is why last year we decided to create an initiative, and we call it Industry 4.0 Big Data and Data Science. And we organized this initiative within the Master of Engineering, of Informatics Engineering. Well, we thought that it would be very important to make room, to create opportunities to discuss the challenges, the developments, and everything that is associated to these important concepts. And today it starts the second edition. Precisely 1 month ago, we had 1 year ago, we had the first edition. Industry 4.0, as you know, is a concept that involves lots of information. 3D printing, cyber physical systems, intelligent machines, robots communicating among them, Internet of Things, sensors. So we are facing something that involves a huge amount of data. That is why, besides addressing the area of Industry 4.0, we crossed it with the transversal field of big data and data science. And we call it Industry 4.0 or Fourth Industrial Engineering Revolution, Fourth Industrial Revolution 1. During the last few centuries, we have been living a few industrial revolutions, characterized mainly by technology that was enabling a given way of organization, a given industry. And the technological revolutions made or meant in the past a disruption between a given technology and a former technology. During the first industrial revolution, the steam engine allowed mechanization. Then we have the second industrial revolution with the mass production. And as enabled technology, we have electricity. The third industrial revolution corresponded to the automation of production due to the electronics and the information technology. And today, the digital transformation is creating what we call a new revolution. And we know from history that a revolution is always a break with the past. New technologies emerge, new models emerge, and this requires new skills and presents new challenges. The model of each revolution we have lived, the three revolutions, has been the decline of well-established industries, and the replacement by emerging technology-driven industries to increase productivity and boost economic growth. With the presentations we have here today and tomorrow, we will better understand this concept of Industry 4.0, the opportunities, the challenges, the risks, the impacts that it means for companies, for society, and for people. Just briefly, I'll show you the program for the next couple of days. We are starting on Tuesday, and we will have 5 days of work until Saturday. Today, we have Professor Goran Putnik and Professor Peter Butaula. We will listen their talks about Industry 4.0 and cyber physical systems, thoughts and questions. And then Professor Peter Butaula will talk about Industry 4.0 and the rising complexity issue in manufacturing systems, how to reduce incompleteness of information, and how to discover new knowledge in manufacturing data. On the second day, Industry 4.0, High Performance Computing and Big Data by Professor Manuel Arenas. On Thursday, Data Scientist and Business Strategy by Engineer Rui Machado. And Friday, Quantum Computing and Industry 4.0 by Dr. Andrés Gomes. And finally, the Saturday, we'll have a very busy day with 4 presentations. ERP in the era of Industry 4.0, 9 years of Factories of the Future, Achievements and Outlook, and then a talk by Professor Levicka about the applied research that has been undertaken within the Master in Computer Engineering, and then a roundtable to finish the whole week of works. And concerning the agenda of today, I will introduce Professor Goran Putnik and Professor Peter Butaula that will make their presentations, and maybe for easier, me and Luis will join the other side of the room. Professor Goran Putnik is a full professor at the University of Minho in the Department of Production Systems. His scientific and engineering interests are in the areas of computer integrated manufacturing, intelligent production systems and enterprises, concurrent and collaborative engineering, enterprise integration, design and management of production systems, agile distributed and virtual companies, and theory and management of complexity in organizations. He is associate editor of 2 international scientific journals and member of the editorial board of several international journals. He has published more than 250 papers and 30 books. He is a member of several prestigious professional societies and scientific networks. CERP, the International Academy for Production Engineering, ECON, European Counts and Complexity in Organizations Network, IFIP Working Group 5.5, Corporation Infrastructure for Virtual Enterprises and Electronic Business. Professor Gordon Putnick collaborates with our master in informatics engineering since the first edition, and I'm very grateful he accepted our invitation to be here on the first day of our Industry 4.0 week. And his presentation is entitled Industry 4.0 and Cyber-Physical Systems, Thoughts and Questions. And secondly, we'll assist to the presentation of Professor Peter Gutawa. Professor Gutawa received his diploma in engineering and Master of Sciences and Doctor of Sciences degrees in mechanical engineering from the University of Ljubljana, Slovenia. He had been active for several years in industry, in particular in the Australian holding company, Ljubljana, Slovenia, managing research and development projects. Currently, he is a full professor of the Department of Cybernetics, Mechatronics and Production Engineering at the University of Ljubljana. He spent some time as a visiting professor at the University of Johannesburg, South Africa. His research interests include mechatronics, manufacturing, remanufacturing, and assembly systems. His current research topics are related to distributed manufacturing, network production, cyber-physical systems, big data, and application of engineering methods to medicine. He participated in several international and national research projects and published over 200 scientific papers and conference contributions. He received several national and international innovation awards, and he is a fellow of the International Academy for Production Engineering Studies. His presentation is entitled Industry 4.0 and the Rising Complexity Issue in Manufacturing Systems, how to reduce incompleteness of information, and how to discover new knowledge in manufacturing data. Professor Peter Gutawa, thank you very much also for being with us today.
Thank you for the invitation.
Thank you very much. It was our pleasure. So, Professor Gordon, we'll move to the other side.
Good evening. At the first place, I would like to thank IPECA this opportunity and this invitation and this opportunity to talk to you. And this invitation had honored me. And I thought, I hope I will present some interesting topics and that we will have some questions and answers at the end. presentation or these presentations. My topic today is Industry 4.0 and cyber physical systems, thoughts and questions. So I will not focus too much on presentation of cyber physical systems, only partially, but the presentations will be in the context of some questions raised from the analysis and from thoughts about the whole movement, which is today characterized as Industry 4.0, and especially cyber physical system as a part of the Industry 4.0. So the cyber physical systems, or by short CPS, could be analyzed at all through the one meta-theoretical framework. And what is meta-theoretical perspective? Meta-theoretical perspective is a critical framework for analysis that create a structure that enables elements of different theories and concepts to be located relative to each other. That means that studying or researching or developing or implementing cyber physical system has different dimensions, very different dimensions. But this meta-theoretical framework, objective of this framework is to make some order and to relate these different dimensions and approaches. So we adopted here some abstraction hierarchy-based meta-theoretical framework. And in this hierarchy, there are different, how to say, themes. First is description. That means cyber physical system definitions, terminology, elements and objects, referring to application areas, models and behaviors. That means how we model that is model related to controlling and to performance measures, mechanisms of choice related to management, methods and tools that we use, and epistemology. There are some more networks levels such as ontology, but I selected not to address them. So this evening I will talk about level of description. That means cyber physical systems definitions. And first question, which I want to put in the context of the title, Thoughts and Questions on Cyber Physical Systems, is what is the true definition of cyber physical system? Actually, we have a number of definitions what is cyber physical systems by a great number of authors and associations, organizations, and there are in some aspects they are different, they are similar, etc. And actually, the question was how we can, how to say, better understand the nature of cyber physical systems. Here are some definitions. These definitions are taken from the keynote paper within the CIRP, International Academy for Production Research. For example, first definition said that cyber physical systems are systems of collaborating computational entities which are in intensive connection with the surrounding physical world and its ongoing processes, providing and using at the same time data accessing and data processing services available on the internet. Then, in other words, cyber physical systems can be generally characterized as physical and engineered systems whose operations are monitored, controlled, coordinated, and integrated by a computing and communicating core. Third, for example, is the interaction between the physical and cyber elements is of key importance. Cyber physical systems is about the interaction, not the union of the physical and the cyber. It is not sufficient to separately understand the physical components and the computational components. We must understand their interaction. Then we have definitions from NIST, National Institute for standards and technology from United States. But it says the cyber physical system or smart system are co-engineered interacting networks of physical and computational components. So you see here, cyber physical system is in a way synonym of smart systems, which is interesting. This is not present in other definitions. For example, cyber physical systems engineering laboratory, also definition of cyber physical systems. So this is also that definition. I will not read all these, and I will pass very rapidly. For example, from Carnegie Mellon University Software Engineering Institute, cyber physical systems are engineered systems that are built from and depend upon the seamless integration of computational algorithms and physical components. Then we have more here. I will come back later. And we have some other principles in the design of cyber physical system. For example, a system of systems is an integration of a finite number of autonomous constituent systems that is embedded system, which are independent, etc., etc. So I will pass here more about these definitions. As you see, there is a lot of these definitions. Also in Wikipedia, we found some definitions. I will not read, I will come later on this. This is by author Edward Lee. Cyber physical systems are integration of computation with physical processes. Embedded computers and networks monitor and control the physical processes, usually with feedback loops, where physical processes affect computations and vice versa. Also here, and these are more. So, for example, this is on the left side. This is one of the most used features to represent cyber physical systems. I will also come back later for this. These are others, etc. So I will not go there just to show this, how to say, richness of this cyber physical. And I will put now question 2. So the first question was, what are definitions? So we see first definitions, the set of definitions and state-of-the-art of definitions, and then we come to the second question. And second question is, which I found, are there any qualitative differences among the definitions of cyber physical systems? I think this is critical question, and following a critical view on these definitions, we can say that, for example, if you analyze these first 3 definitions which we said, for example, cyber physical systems are systems of collaborating computational entities which are in intensive connection with the surrounding physical world. So the focus here is on connection of computational entities and cyber and physical world. Of course, we have data processing services over the internet, which implies big data and cloud computing and this type of stuff. Then we have here CPS can be generally characterized as physical engineering system whose operations are monitored, controlled, coordinated, and integrated. This is actually almost the same as the first, which is collaborating computational entities in intensive communication with the surrounding physical world. This third is very similar, if not equal. And here is what are first on the left side is actually scheme which corresponds to these 3 definitions which I referred before. And on the right side we have diagram of industry of comparison of industries paradigms from industry 1.0 to industry 4.0. And one of the differences which could be measured and which could be described is complexity actually here. So the qualitative difference between these paradigms, Industry 1.0, 2, 3, and 4.0, is actually in complexity. So for each subsequent paradigm, complexity grows, and this growth is not linear. Actually, we can say that for Industry 4.0, complexity is by the order greater, or by many orders greater than complexity of paradigm Industry 3.0. This is important because I will say later why. But for example, definition of cyber physical system for Wikipedia. Here is one word marked yellow, word phrase marked yellow, which I said interacting with each other, computational resources and computations with physical world in myriad ways that change with context. This is important. This is important that system is not fixed. That means when we implement one cyber physical system, this is this critical difference of this definition comparing with other definitions I referred before, that this is in continuous change. That means that each other changes. So the computational worlds and this interaction, for example, if we start with one computational structure, implying or structure of computational resources of the algorithms of the models, it means that in the next instant of time, it would be changed. So this is feedback that actually generates a new structure. Here is also by Edward Lee, author. They said that where physical processes affect computations and vice versa. This is very important. So this means that cyber physical system should have capacity to be changed by itself. So you cannot have a fixed program run along the time, but program that will change itself. And I found this is a critical feature of cyber physical system. So definition says also embedded computers and networks. These are what I showed earlier, but I just highlighted this part. Embedded computers and networks monitor and control the physical processes with feedback loops where physical processes affect computations and vice versa. So this is quite different than this here. This is on the left side is purely one integrated system consisted of computations, communication, control, information, physical objects, etc. So this is practically traditional computational system connected with sensors on physical objects and which is subjected to some control algorithm. Difference is that actually here we have the system which can change itself, by itself, can be changed by itself, which is totally new computational paradigm. So it is not traditional computational paradigm. So that means that if we have here a picture of one Internet of Things, what does it mean, Internet of Things? This is a set of sensors. Of course, this set should be very large, very large. That means at least thousands or millions. Also, this could be represented, if this is abstract interpretation, its interpretation could be a large network of enterprises or large network of processing or production units. So this is a physical world. Physical world, that means is equipped with sensorial systems and systems for collection of data about the physical world. And here we have model of this physical world. So this is simulation model of this physical world. This physical world, this is information or cyber model of this world. So in fact, these two models must interact. These two models must interact each with each other. So this is more or less in this way. Or along the time, it would be practically we go through sequences of collecting data from physical world, and then we have simulation processes. Then we collect new data. Then we have new simulation processes for decision making, etc. And so on. The question is that actually this picture is not good, because this picture is just deterministic. That means that we have just interchange between these phases, but we need a new picture, for which we do not have graphical language, correct graphical language, and this new picture should include changes by itself. So that first simulation actually changed the physical world and changed itself as a model. So that means that this software actually changed itself by itself. So and this picture actually does not represent. Now the question is, so this is actually one other picture. So we have here one point from which we make simulations for different scenarios, and we have that based on our some information or perception of world, etc. We can make decisions based on these simulations. This is actually what is here presented through collecting data from physical worlds. Then we have simulations and so on in sequence. However, the question is, what is the time interval between these two actions, or between the collection of data and simulation? So is it 1 second? Is it 1 hour? Is it 1 day, 1 week, or whatever? However, recent research shows that the real-time management model is superior, or at least not worse than the horizon-based planning or control of production in turbulent environments. Because if we have fixed environment, we do not need Industry 4.0. If we have fixed environment, it is just a question of fixed automation. The problem is actually turbulent environment, for which we need all these new concepts. And for example, here are paradigm. I cannot show you. Some pointer. So here are for example, planning or scheduling of production based on fixed horizon. So we have here some horizon, and we plan this. How we plan this? We plan this through use of some planning algorithms or by simulation. So we simulate. So this is what we have here. So we have data here, and then we make simulation for making decision how production will be controlled in the frame, for example, of 1 day or 1 week or 1 month, etc., whatever. So this is here. So this is show that this actually cannot stand this type of planning, and then we introduce little bit modify this planning fixed horizon planning with reconfiguration. So at some moment we decide that it is not going well as we plan, then we make replanning, etc. So, but always until the end of horizon. Some improved methodology, which is today very, very popular, it's called rolling horizon. So rolling horizon do not plan the whole horizon, but some part of horizon. Then after that, in the middle, maybe, for example, some moment we make replanning and so on. So we have here our position of this planning. But real-time management is quite different. Real-time management do not have planning horizon as here in these paradigms. This is conceptual scheme, but actually here is making action in each moment. So immediately after collection of data, we made a decision based on simple calculus of the best possible decision of selection of resources or plan in this moment. So you see, you have practically real time is every second you make a decision without planning, so no planning. And the interesting is that this research shows that this approach is even is better than these approaches when environment is turbulent. You see. So if this is true, so we come with this approach of real-time management, we come to the kind of real-time data-driven production, of data-driven management of activities in our organization of production. Production control without planning and consequently without need for simulation. Metaphorically, due to emergence of the big data, some researchers and thinkers claim we come to the end of theory. So the question is, if real-time management is superior, then why we do need cyber-physical system? Cyber-physical system is one of the main features of Industry 4.0. See, but this is controversial now situations. We show in research that real-time management is superior than any method that performs some planning. In simulation, in cyber-physical system means we have here we copy data, then we make simulation plan, and then we run production in accordance with the simulation results, what simulation said us, etc. What is the best and that way. But actually, with this paradigm, it is shown that we do not need any planning. So we do not need any simulation, any interaction with the simulation. So why we do not cyber-physical? So you see, first question was about definition. Then second question was about the true definition. True definition must imply some qualitative difference in computational paradigm. But the third question is why we do need at all cyber-physical system if the real-time management actually shows us that we do not need any planning and any simulation for that. So this was the questions which I found interesting along my research and research by my collaborators on these cyber-physical systems. And now, so considering real-time management and especially considering growing complexity. Actually, complexity, there are also several definitions of complexity from the engineering point of view and from computational theory point of view, which is like the information systems point of view. Each object has its complexity. For example, this bottle, which is very practically simple, has its complexity measure, which is very low. So it is object with complexity, which is very, very low. But from the management sciences point of view, this is not that way. The management science says that actually complex systems starts only when we are presented to, or we witness phenomena of emergence and self-organization. And these self-organizations could be interpreted that software in cyber-physical systems reorganized or redefined or restructured itself by itself. So only here we have practically complex system and maybe cyber-physical system. So, but if we have emergence here and self-organization, then we do not need simulation to make decision. Because if you make decision for some period, during that period can happen something new, emerge some new concept, and can happen self-organization. So really, the question is why we don't need cyber-physical system. And this is the questions I wanted to put. There are many other questions. For example, question, what is the relationship between Industry 4.0 cyber-physical systems and Internet of Things and ubiquitous and cloud manufacturing, and many other questions, but I will stop here. So my question would be, what is the true definition of cyber-physical system, and really, do we need cyber-physical system for today? Okay, thank you very much.
Okay. No, thank you. Good evening to everybody. I was already introduced, but let me say I'm very pleased to be here today. I'm here by chance because I'm making a mobility project. That's why I put all these logos here on. I have to put it. This is where I get my money from. Cable. Should I stay there? I stay here. Okay.
Try again.
Okay, try to not to move too much. So I'm on a mobility project at the University of Vilnius, kindly invited by Professor Putnik. We are good friends for years already, and we are also members of the same academy where we meet occasionally. And he organized a very nice general assembly of this academy just 2 years ago. It was really very well organized, so all the congratulations for that moment. Anyway, and he also made a kind of introduction to my topic. My topic is related to complexity. And of course, because Industry 4.0 is very popular now, modern, I connected these two words together, and we noticed that Industry 4.0 concept is increasing the complexity. But we are looking for the answer, how to how to manage this complexity, which of course is making us problems, headaches, especially in the industry, where this perhaps they even don't notice that the problems is lying in the complexity issue. So, and we are working in my group. I have a small group of researchers and with PhD students, mainly in this direction, how to manage the complexity. And I think one of the, or two of the ways toward managing the complexity are how to decrease the incompleteness of information. We are always dealing with incomplete information, but what we would like to achieve is to make these incompleteness lower, less. And the other thing is how to increase the amount of knowledge which we have. And for both of these, let's say, things, data are very important. But before going into this details, I will show you, because I don't know, of course I have to move it to this further on. I wrote a short abstract for this presentation. I will read just the first sentence of it, because I think it's very interesting. I don't know if everybody knows that, but the Industry 4.0 as an indicator of the fourth industrial revolution is still about to happen, because it was introduced by our German colleagues, academicians and engineers just a few years ago. I think it was in 2011 or 12, as an idea for provoking their politicians that they should do something about their leading position of industry. And this now emerged into really a new paradigm. As I'm going around the world, everybody's talking about Industry 4.0, but it was just a provocation of our colleagues. But remember, 2011, 12, that was the deep most point of the recession at that time. And the industry was not doing well. I remember our industry fell down for about 20% just over the night. But our German colleagues, they were clever. They went to Frau Merkel and asked for money, and she gave right away €500 million to our German colleagues. And now if you go to international conferences, you will notice that most of the participants, or even half of them, are coming from Germany, because they have to spend money, and they have to show the results. Okay, just for the beginning. Anyway, about what will I talk about in this my presentation? First, I will, of course, ask myself a rhetorical question, which is important for all of us. Why research into manufacturing is important? Why should we do this? And then I will share some thoughts about my perceptions, what Industry 4.0 is. And then I will enter this subject of growing complexity and how we can reduce the incompleteness information and how we can improve our knowledge. And I will show some examples from our research. Well, there is also a list of papers. I'm ready to give this presentation to students if you are interested in. And there is a list of publications for your further reading if you are interested in this topic. But let me go first to this question: why research in manufacturing is so important? Of course, manufacturing is generating new value, is generating wealth, and that's very important for each nation, from developed or underdeveloped nations. So, and we should know that, of course, also the power of a state depends on the industrial capacity of that particular state. And if I look from our perspective, Slovenia is a small country, 2 million people. So I think like a mini region or something like that. But we have strong industry, which is supplying mainly. We don't have many OEMs, unfortunately. Having OEMs is very important, because then you don't just sell your work, you are selling your brain potential. So this is why it is very important to make research in manufacturing in this direction, because the power of the nation depends upon that. We are trying to also convince our politicians, but we are not so successful in this as our German colleagues, unfortunately. And if you look a little bit into the figures, in the European Union, about 22% of GDP is generated by manufacturing industries. On the global level, this is a little bit less, about 16%, meaning, I don't know what, I didn't, I hope it counts. Okay, it counts. I have to step back a little bit. Meaning that there is a lot of potential for those countries, especially for countries in development to step into this direction, to increase their manufacturing potential and power. I spent some time in South Africa. That was very important. I think we recognized the potential which they have, because they have a lot of natural resources and they have a lot of young people, which we are suffering from, especially in Slovenia, or the aging of population is a very critical thing. Okay, but we, on the other side, we can see on the global scale that there are countries which, I remember China 20 years ago, there was nothing. Now there are giants in manufacturing. Korea did, South Korea, of course, did a little bit earlier. So we can really see from these examples that developing of manufacturing industry is key for a country. Okay, now let me go to, this is a well-known picture. I borrowed it from my German colleagues. But what I want to show you with these pictures, what really happened during the previous revolutions, which are recognized afterwards. The fourth one is forecasted to happen. So during the first revolution, the mechanization of work happened. So the power of people were exchanged by machines. What happens in the second revolution? The organization was much improved based on the scientific principles of Taylor. He wrote that book at that time, but Henry Ford was the guy who implemented it. So organization and fixed automation of work. You remember those lines of assembly, lines producing Ford Model T? That was that solution. So the 70s, 60s, 70s brought industrial robots, CNC machines, and this kind of flexible automation. That was also a revolution. We took a part of that already. But what is really the major, let's say, breakthrough in the fourth revolution, I think it is digitalization, but not only digitalization of processes, or is cyberization. That's what Professor Putnik was talking about. So we cannot digitalize everything, but we need a kind of combination of humans and machines in a cyber-physical system. Okay. So when I was, starting to talk about this subject to my students on the master courses at the University of Ljubljana, I was looking for a good, I'm using pictures a lot, and I was looking for a good figure showing what really Industry 4.0 means. And I found this picture from Roland Berger's study just a few years ago, which is indicating what is the key. The key is the connection among the suppliers, the customers, the producers. Everything is connected. And then there are some new specific technologies, like, for example, additive manufacturing. It's a booming technology, and it also can be contributed to Industry 4.0. And then we have, of course, big data. We will talk about big data today. And of course, all this cyberization is opening the issue of cybersecurity and so on. So these are, I find this figure quite good because it's indicating the key technologies, it's indicating that everything should be connected. Okay. But what is of our interest is how the role of human being is being changed during these revolutions. If in the first revolution, we are indicating here subject meaning human beings, operators, work managers, and so on. It's not an individual, it could be a team. So in the first revolution, everything was done, or before was done by a human. Also the force of doing processes was generated by humans. But then gradually, human stepped back from the process because the machine took over then the execution of the process, And then we got the controllers, these numerical controllers or computer controllers, which take over the control of the machines. And then we got the system for monitoring, for supervision control, and these kind of things. And what is saying to our subject in the fourth revolution? He will become just a manager or knowledge worker. So two roles. One is knowledge workers, and the other role is decision makers. So that's what is expected. So the people will be really moved away, and then you can make on the beach your work. Everything that will be possible because of the remote access and so on. But that's a little bit futuristic. Let me show you my concept, or the concept which we have developed together with my doctoral student, the concept of cyber-physical system. If this is our working system, it consists of a physical part, that is the machine, that is the controller of the machine, and that is the process. The process is important because it's generating new value. It's transforming a blank into a piece and so on. So this is a physical space, we say. And here the physical relations are. And then we open the social space, because some people, we are also physical. But our communication to each other is much different as on this physical level. So that's why we opened here the social space and the social system which is connecting the people in a, let's say, in a factory or in another community, whatever. But in between, we place this cyberspace in which the cyber system is positioned. And of course, there are communication from physical to cyberspace and from social to cyberspace over special interfaces, which can be very advanced or will become very advanced in the future, like augmented reality, virtual reality, and so on, or subject to cyber system, and so on. So that's our idea, and of course, everything connected over the Internet of Things. That means interconnection among the basic elements, Internet of Services, Internet of production networks, or whatever. So this is our concept, our idea. It's not worked out yet because this student is working too slow, from my point of view. But this is the idea which we have behind. Okay. Now let me go to the complexity issue. Professor Putnik showed us already that the complexity is growing from revolution to revolution. I even think that the first step was toward the decrease of complexity. Why? Because, like Henry Ford did it in his Ford factory, everything was repeatable, everything was the same. Every part was the same. Every movement of people were the same. And they could learn that in 3 hours, he said. He said, I can take everybody from the street, teach him in 3 hours, and he will repeat it forever. So that means zero complexity at that point. But with flexible automation, with variants of products and so on, this started to increase again. And now with the fourth year of revolution, I think it will again increase. So that's the problem. How can we tackle this problem? That is the question here. So let me go into a little bit of definition of complexity. I don't want to read much, but I think this sentence is very important. The first one here, which says, at each level of description, then, there are many important features in the world around us that are fundamentally unpredictable from the basic laws of physics, but depend on the accident of the particular universe. So we cannot describe by laws of physics. It's not a problem, it's not a deterministic problem. There is a lot of uncertainty. All this is said in this sentence, which I took from the literature. There are some other definitions below, but what is interesting is, if you have several elements, and if you look into your factory, there are many elements, and they are interacting with each other. And those interactions are bringing the complexity. Okay. I had one student, he's still in my team. He studied the complexity that Eleonowski, of course. He studied this phenomenon of complexity a few years ago in his PhD. And what we really discovered, if the process is totally random, like, you know, if you make a draw of a coin or something, it will either fall on one side or on the other. It has nothing to do with complexity. Or if the, you know, if the system is totally deterministic, nothing to deal with complexity. But here in between, we are the problems. And that's why we say in production, we are always on the edge of chaos. Because all things are happening at the same time, problems arising and so on. The suppliers are not delivering work, a worker is ill, and so on. The machine is broken. All these things are happening. And we say this is, that's why we are here in production, and that means complexity. And this point is, you know, the edge of chaos, we say. And it is uncomputable beyond that point. What we try to do in production is to drive this, to drive this, you know, problems toward, let's say, more deterministic situation, to periodicity. Like in the air traffic, for example. On one day you have a terrible weather and all the places are in delay. But over the night things get together again, and in the morning they start according to their schedule. And it's this repeating day by day. So this kind of periodicity we also have in production. Working week, working day. Usually we don't produce 24 hours, 7 days per week because very rare industry works in that sense. So this periodicity already brings a little bit of order and so on. So, but that is the phenomenon which we are studying. And of course, if we are studying this phenomena, we should look what are the drivers. And we can recognize there are drivers of complexity from the outside world, which we cannot, you know, do something with about. But if we know, if we understand, and if we perhaps even maybe able to anticipate, then we are in a better position than as our competitors, for example. So what are the outside drivers, like global competition, right? Like abrupt behavior of markets, like uncertain environments, like interdependence risk because of the cause and causal relation, what is the cause and what is the result of that, and so on. But there are also inside drivers. And if our managers, we have to deal something. We have to do in this direction to reduce this the influence of these drivers. And certainly one of the main drivers inside is the inefficient and reluctant to control hierarchical structures. People in general will reluctant to control, resist. We don't want to take over, but yeah. And this is one of the causes. And the other is incompleteness of information. I already said that at the beginning. Usually we are dealing, we are deciding, we are making processes on incomplete information. And if we can do something in this direction to make this incompleteness less, we can do something. And another driver is insufficient knowledge. If we don't have the knowledge, then we also deal with the complexity, much more focused out. And insufficient understanding of the same phenomenon, of course. Okay, so these are the drivers, and we in my group we are dealing with several projects. I put some of them which are addressing this phenomenon. First, to understand the phenomena, and these are papers which we did together with my colleague, Dr. Babic. And then we did also some work in the direction of simplification of structures. That was done already with my colleague, Professor Stuga, who retired in between, and also my predecessor, Professor Petlenik. who started this study of this issue of complexity. And then we introduced some autonomous elements which are much easier to be controlled and much more flexible. We also have some papers in this direction. And then in the last time, I think we are working in the direction of reducing incompleteness of information by collecting data in production. So by collecting data in real time, we decrease this incompleteness. And then, of course, when we have data, then we can learn on that. We can use data mining, we can use the knowledge discovery techniques, which are very useful. And the term big data then comes out. And we also do some recent studies in this direction. We did also some study or research in the network structures. Also one very interesting paper together with Professor Putnik 2 years ago or 3. And what is still ahead of us is how to introduce self-organization, which I think for cyber-physical systems will be one of the key features. Okay, so that's what we are doing. What we are doing, I will now go a little bit into this, our studies. First of all, how we go forward in the direction of simplifying manufacturing structures and how to make them more autonomous. And yeah, we got the motivation from this research from the 70s. You know, these Swedish companies are very ahead in some things. They are very well developed. And they already tried in the 70s, I think it was in the Volvo company, to reorganize the work from this assembly line, which was typical from the Ford time, into a little bit other configuration, letting the people autonomously decide, working groups and so on. Perhaps it was a little bit too early, but they did this trial. And we see a big motivation in this sentence that we go from simple jobs, as was the case in Ford factories. 3 hours learning and then repeating. That was very simple task. From simple jobs in complex organization, but the organization was very complex, to complex jobs in simple organizations. Then this transition, and we saw this high motivation for our work, and we went into this research, and we developed the concept of so-called autonomous work systems, which are somehow small enough, self-sustainable, can be managed, and so on. It's a kind of between the single machine, let's say, and the factory as a whole. So it's something in between. I won't go into much detail here. I will just show you this concept which we developed. So this is our autonomous work system with several elementary work systems, which are meaning machines with processors and so on. And of course, there are some managerial functions. There is an integrated data and knowledge base. But what is here interesting is this feedback. We introduced the monitoring function. And thus we introduced the feedback, which is really in real time helping us to plan and control the system much more effectively. Okay, so that was the basis. And the basis was then to develop the monitoring systems. And that was happening about 10, 15 years ago, when in industry there was no this kind of monitoring systems or feedback systems applied yet. That was not the case. So we started this project. We show you some results of that project on online monitoring of operations, processes, and resources, and the environment. So that is one of our skills, how we implemented it. So the idea was really to close the loop and to obtain this goal-oriented closed-loop control. And how we close the loop? We introduced the so-called production data acquisition terminals. like touch screen. That was quite modern at that time, about almost 15 years ago when we implemented it. And so the operators were, getting the information over these terminals, but also putting their information in when they started a new job or finished the job and so on. Okay, and then they also collected some, if possible, of course, because the CNC controllers are very close. Siemens, Fanuc, and these kind of producers, they don't want you to get information out. Very close system. But sometimes you manage to get some information out, or you put in parallel some sensor just to collect certain values or certain parameters to obtain this data. And we also then close the loop with an ERP system, which was running in the company. And we implemented this in the company. And that are some pictures from that implementation. It's implemented in the company Vitoster Power, which is producing water turbines. That's their major, let's say, product. They have installed, I think, about 3% of the whole globally installed power on hydropower plants, so they are a player. And they have one-of-a-kind production, engineer-to-order production. And we implemented, this monitoring system. Later we called it manufacturing execution system, because it's not just monitoring, it's closing the loop, also for control. And here are some pictures. This is, for example, a picture showing, this is the layout of one of the workshops. And these colors are meaning something. If it's red, then it's not good, that's for sure. But if it's green and yellow, I think it's good, it's running. It's in operation, and that is running and can be observed from anywhere, because right away, 15 years ago, we implemented it as a web application. So I think that it was one of the first on the world in this direction. Then when we noticed that it's a good solution, we went to another project, another production systems, and this is the case of die casting machine cells, which are producing aluminum castings for automotive industry. So very different production process as in engineer-to-order company. And we also implemented some sensor. In this case, it was good because the developer of the cell was our partner in the project. So we got all the information from the controller, which were already processed from them, available. And that was a very good improvement in this direction. Then we noticed that it is an interesting approach, what we implemented. So we went to another process, to a welding process, again to this, back to Vitoster Power. And there you see these big welding parts welded together that are turbine parts. And you know how this is welded together? Because it's so big and it needs so many welding hours, there is a group of welders which attack the part from different, let's say, points. So it's a kind of a cluster. And we were asking ourselves how we can follow this. They are manually welding. So they are bringing the welding devices with them, and then they weld and they go to another place, to another, and so on, because there should be some waiting time or cool down time or whatever. And we, at that time, implemented the wireless technology. The ZigBee, which then collected from these welding devices. This is one welding device, and what we were measuring were the current and the voltage, which are very indicative parameters for the process. And we implemented it, and the idea was to automatically, that was digitalization, you see, automatically fill out the welding diary, because it's a very important document which should be produced. But usually they do it by hand. In this case, we did it through automatic monitoring, also automatic establishment of this welding diary. So then, of course, new project came in, and the next one was on water turbines. That means on the products of the Litostar company. So we said, okay, we are able to monitor your processes in production. We are sure that we can monitor your processes on your products. And we close the loop in so-called product service systems. So the idea was that Litostar would not only offer the hardware, the turbines, but that they would be able to follow, to monitor in the operational phase the product, and accordingly then suggest maintenance and this kind of actions, really to achieve the best performance of their product. So we implemented that, and I think when I reported that, I think it was in 2014 on a professional conference, nobody else of the competitors was on that stage. Unfortunately, then next year the owner was changed, and the new owner has no, he didn't recognize this yet. Okay, so these are some examples from that project. It's implemented on one of the hydropower plant of our Sava River in Slovenia. Okay, but now let me go to, so that's how we collect data and how we decrease the incompleteness of this data. But can we now do something with this data else? Can we squeeze this data and learn from that? That's the idea. And okay, then we studied where do we have the sources of knowledge in manufacturing. And of course, we discovered that we have some external sources of knowledge. One is from, let's say, from research and development, for books, from papers, reports, and so on, but also people from educational bring the knowledge. But we ask ourselves, okay, can we also learn something from this process itself? Of course, we have the learning by doing process. When people are working, they learn, and they are better. Then afterwards, we can also have learning by researching. But what was for us interesting was so-called self-learning. That meaning, can we learn from data, which we collect, as I showed you, in different systems, in different processes. And we extended our concept of autonomous work system with the learning loop. So we added this learning loop. We are collecting data from devices, from processes, from workpieces, from operations, from the environment. We are storing this data, but afterwards we trigger this data mining and knowledge discovery loop to find knowledge in our patterns. That's not replacing the basic theory. So that doesn't mean the end of the theory. It was pointed out by Professor Putnik, but it means an additional source of knowledge. Of course, it's empirical. It's based on empirical measurements, but it's an important source. And of course, now we are studying this. I have a new PhD student. He's very creative in this direction. And last year we published 2 interesting papers on the pulse diagnostics in plastic injection molding. So plastic injection molding is a quite oftenly used process. I think I have here one slide showing this process. Okay, now okay. So this is the die casting process. Here is the die tool, and here is the extruder pushing the melted plastic material into the closed tool. Of course, the tool must be closed, and these are the parts which are coming out of the process. The problem, there was one master student working in that company and doing his master studies, and he collected data from the controllers of these machines. And there were about, I think, 2.5 million of cycles of data for 2.5 million cycles collected over half a year on 5 these kind of machines. So that was the basis. But let me show you what was the problem with this data. The problem with this data was that, okay, we wanted to see if we are able to forecast a certain deviation, failure. failure on the machine, because that's important. If we can forecast in advance, then we can remove the cause. Stop the machine, do something, because if the machine stops due to this failure, then to start it again takes a lot of time. And you make a lot of scrap in between. That's the problem. But the problem here is that we have the density of data. That means the ratio of about normal cycles and faulty cycles is very high. It's, I think, about 1 to 1,000 or even more. So you have a very low number of cycles indicating failure in comparison to other cycles, which are good because of the performance of the process. But the question was how to use this data despite this fact. Of course, we did some analysis, and we also tried the so-called machine-to-machine communication approach. We asked ourselves, can we learn from data from one machine and use this knowledge on another machine? By, communicating this data via machine-to-machine. So that was our research last year, and it was then published in the same Annals, and we found out that we can investigate, of course, data from one machine. We can also join data from several machines, and we also can learn. Even we can learn better from that, but we can also use the data to machines which are not involved in the learning process. I think that was very interesting, and I will show you what was here the idea. The idea was really to make this learning of each individual system, and also to make this learning on the combined database. And what we see, I already spoke to the producer of the machines. They showed some interest, but they were not so excited as I would expect from that. Because they're producing thousands of these kinds of machines per year. And we show them that they can learn and use this model of knowledge to machines like tabula rasa, without any prior knowledge. Okay, so that was a process. First, of course, we have to, there's a lot of data pre-processing and preparation and so on, and then the mining and so on. I don't want to go into this detail. If you are interested, you can read the paper, which is given in the literature behind. And these were the data which we were basing on. So most of the data came from the controllers. The controller itself collects data, but the way of collecting is that they cover over. A new cycle comes and it's covered previously. So it's a kind of buffer. But this colleague, the master students, went each day to the workshop, and because for one day there was a buffer, collect for that single day the data on a memory stick and brought it to the computer. And next day again, and then again, half a year. That was quite a tedious work. But that was the only solution. Then we, of course, we analyzed this data, and we added some manufacturing execution data, because it was interesting for us when the tool is changed, which cycles belong to a certain tool. That's very important, because tool is of this issue. Important is this in this process. So this is now the data about the data. 2.2 million cycles over 6 months, over 5 machines with 83 different tools. And the ratio of normal to faulty was 1,500, almost to 1. And if randomly probability of guessing or forecasting the failure would be 0.07%. Okay, then we make this analysis showing this cross correlation. So all the data from one machine, how it would be the model on one, from all machines on one machine, and so on, all these cases, and these are the results. Of course, the results are not so, let's say, extremely good yet. But we can, in certain cases, with certain probability forecast the failure. I won't go into the details. The numbers are not so good, but it's much better as just randomly guessing. But there is still a lot of room to learn from. So, okay, there were some. I don't want to go into the details because I think I'm already quite long. But let me go to the conclusions. So I wanted to present you our motivation. So we didn't take Industry 4.0 as now let's jump in, because we are working in this area, because this is the area of complexity in manufacturing. Industry 4.0 came by just by chance, but we see quite a good motivation for young people, for example. Now my colleagues are talking about that students, again, are interesting for engineering because engineering is becoming appealing because of this cyber-physical, smart, big data, and so on. That is a good one. Another thing is that also the politicians now, they are talking about Industry 4.0, not only in Germany, but also in other countries. From Slovenia to South Africa, if you want. That's also a good point. But as I say, I think the phenomena which is interesting behind is the same. It's the complexity, but it is even increasing. So, okay, and I show you some examples of how this incompleteness of information can be reduced, and also how we can learn from data, which I think these are promising results. Okay, so I told you I put some papers of our group in this list, and I'm proud that most of them are published in the Third Annals, which is the very distinguished journal, but also others are quite distinguished journals like International Journal of Production Research and so on, or Advanced Manufacturing Informatics, or this kind of journals. So this is the list. If you're interested, I can give you this presentation, also this list. And if you have further questions or also communication, I will be here till the end of April. So if you're interested, you can visit me at Minio. I'm sure that it's possible, and we can have the discussion about if you are working in this direction. And thank you very much.
Thank you, Professor. Thank you, Professor Gordon. We can have now a short period of time for questions. Any comments?
Should I stay here?
Yes, you can stay there.
Okay.
Any questions for this professor? Any comments? Commentary on something for?
I know it's late and you are tired, but try to provoke you a little bit. I have lots of sense.
É importante ver qual No?
My offer is still open, so if somebody has interest, would like to contact me, I will be in Guimarães till the end of April.
Perceberam? Ele está connosco até abril, mas sim, pouco por hora. Vai ser dado o contacto dele também. Se quiserem contactá-lo. Nós vamos com muita frequência a Guimarães. Nós, se quiserem ir connosco, temos todo o gosto disso e é fácil para o trabalho, não é? Então, vamos todas as semanas. Okay. Professors, thank you very much for your presentation. Estamos cá amanhã de novo, tentando não desatrasar os hoje, outras 7 horas. Vamos ter connosco o professor Manuel Arenás, professor da Universidade de Coruña, também de uma empresa que trabalha na área da computação paralela, que é uma área muito interessante a utilizar-se com indústria. Acho que é um tópico também, na minha opinião, de interesse para alunos que estão nas nossas engenharias. Não para empresas também. Obrigado. E também é. Está bem? Miguel, tiraste uma